the risk factor increases probability of the outcome, protective factor decreases probability of the studied outcome. Obviously, we would like to have less risk factors and to have more protective factors. So the question, when will we prefer the use of, will it be enough to use risk factors? So the answer is very simple. We come to the question about modifiable and non-modifiable risk factors. If it will be quite easy just to control them. In other words, we can modify or reduce the impact of these factors by some intervention. For example, if a smoker decreases number of smoked cigarettes per day, we make modification of risk. And obviously, smoking is a modifiable risk factor. Any behavioral factor is modifiable because we can change our diet, our dietary habits. We can change our sedentary lifestyle. We can change our habits. Just there must be willingness to change this, and we must take some efforts to force ourselves to be confident in our decisions about changing behavior. Another situation is when a risk is not modifiable factor. For example, we all get aged, okay, and suddenly we understand that we are not young anymore, but age becomes the risk factor. Possible to change the age, for example, in the elderly people. So the only thing which we can suggest for them is to add protective factors. Unmodifiable risk factors include family history, gender, race, ethnicity, things which are biological factors, which we are not able to change. For example, our anthropometric parameters, let's say the height is something which is predetermined by our nature, our heredity, our biology. We cannot change. If you know that tall people are more predisposed for the certain disease compared to short people, that's it. The only thing we can do is to add. Hope you got it. And now we come to measurement of risk by epidemiological methods. So when we talk about risk in epidemiology, we understand probability, again, probability, but probability of developing a condition. And the key word here is over a defined period of time. The point is that the time is a very important factor. Let's say we study probability of developing a disease during a year. That will be one parameter. If we measure probability of developing a disease for 5 years, or maybe 10 years, or maybe during all the life, which is called lifelong risk, it will be completely different. So that is why in a definition of risk in epidemiology, we add the parameter of time. So risk is probability of developing a disease over a defined period of time. As you already know, for most of situations, for most of conditions, we study risks by incidence. That is why we measure risk for those conditions for the period of 1 year. So we can measure risk of getting a disease in 1 year period of time in the studied population. However, it's not always correct. In many cases, when we study chronic diseases, for example, when we study risk of diabetes mellitus or risk of stroke or risk of oncologic disease, we don't want a probability for a year. We would like to know probability of developing a disease for the certain years. And usually it will depend on the age when people are the most likely to develop a disease. So, for example, if you know that disease is typically detected at age of 50 to 60, we would like to know the risk of developing a condition over the next 10 years. And then we can make better prognosis of population, which will be at risk for our intervention programs that we must probably suggest. Okay, so if you look at the formula, and it is given here, number of people who develop disease in a certain time, and we must divide it by number of people which are free of disease at the beginning of the studied period. That is risk or probability. So you can see that incidence of disease is a direct measurement of risk. For example, if we want to know risk of developing tuberculosis in the studied population, we will take number of people developing TB in 5-year period and divide by number of people who don't have this pathology at the beginning observation. For example, if we have a 1-year follow-up, which means a cohort study of people for development of coronary heart disease, and we take 3,000 smokers and 5,000 non-smokers. In order to calculate risk, we will calculate incidence. The first parameter will be incidence among exposed population, which means incidence among smokers. So you can see in the table, we will take 84 subjects who are smokers and who developed coronary heart disease after 1 year of follow-up. We divide this number by 3,000 of smokers. In other words, we get absolute risk, incidence of a disease or outcome among people exposed to the risk. And you see it is equal 28 per 1,000 of people. If you look at the second parameter, we call it incidence in non-exposed population. We can compare it with the previous one, and calculation will give us 87 over 5,000, which means number of people who developed coronary heart disease among non-smokers, and the result is 17.4 per 1,000 of people. So this is absolute risk of coronary heart disease among people who are not smoking. If you make a comparison between these parameters, we will get relative risk. So relative risk is a ratio between probability of developing a disease if risk factor is present over probability of developing a disease if risk factor is absent. So, example, incidence of stroke in hypertensives, and we compare it with incidence of stroke in normotensives. If we divide one parameter by another one, we will get measure of risk. Risk difference, or the parameter which we can calculate on the base of it, can be also calculated. Risk difference will be the subtracting of parameter of incidence among exposed, which is 28 in our case, and incidence of non-exposed, which is 17.4. So 28 minus 17.4, we will get 10.6 per thousand. And risk difference is used to judge about the scale of the problem. For example, if you calculate it, you can say that for every 1,000 of smokers, 10.6 more cases of coronary heart disease develop among them compared to 1,000 of non-smokers. To judge by risk difference about epidemiological differences is very difficult. So that is why we can use another parameter, which is called attributable risk. It can be calculated on the basis of risk difference. So in our example, relative risk was equal 1.61, while risk difference is equal 10.6. About relative risk. In relative risk, we have interpretation. We compare it with a parameter of 1. So if relative risk is more than 1, we say about positive association between exposure and outcome. If you have relative risk more than 1, it is positive. Less than 1, it is negative. And if it is equal 1, there is no association between the studied exposure and outcome. Situation of relative risk less than 1 shows presence of protective factor. That's a situation when presence of the factor which we study decreases probability of the outcome. One more measure of risk is called odds ratio or relative odds. The odds means the ratio of probability of occurrence of event, non-occurrence of event. So that is why when we make a calculation of odds ratio, we have to pay attention to our 2x2 table when exposure and outcome are located at corresponding cells. So we take A, B, C, and D to calculate odds ratio, and the formula will be A times D over B times C. And this parameter AD over BC will give us odds ratio that is approximate measure of risk. Okay, for example, 1 minute. In some cases, odds ratio is exactly equal to relative risk. Usually, it is the situation when outcome which we study is relatively rare. For example, we study then in our 2x2 table, there is no difference between B and A plus B, D and C plus D. Another factor which is important to have equality between odds ratio and relative risk is that cases should be representative of all cases in the population. And then controls should be representative of all known cases. So it's a matter of proper sampling and proper selection of subjects for the study. Okay, so if we calculate odds ratio, we say that it can be a very good measurement of risk, particularly in case control studies. And if we have odds ratio for a cohort study, it is not very meaningful because in cohort study we directly calculate risk, but in a case control study we can calculate risk using prevalence of exposure for cases and controls. So then in a case control study it will be a very useful measure of association. The problem for retrospective studies is that relative risk cannot be calculated directly. So if the incidence of disease is relatively low, odds ratio will give us very accurate estimation of relative risk. Okay, so for example, we have the situation when we study by 2x2 table, history of sexual abuse and attempts of suicide. So we construct 2 by 2 table where the cells are filled 14, 9, 49, and 149. So we calculate relative risk of suicide attempts in subjects who had history of sexual abuse and those who didn't have. So you see, incidence for the first one is 14/23 because those are subjects who had history of sexual abuse. And the second parameter of incidence is 49, which is cell C, over 198, which is the total number of subjects without history of sexual abuse. And the result which you get is 2.46. That means people or subjects with a history of sexual abuse have 2.46 times more probability of committing a suicide compared to subjects who don't have history of sexual abuse. If you calculate odds ratio by the formula, we will take 14/9, divide by 49/149. You see, odds ratio gives the result very different. It is 4.73. So if relative risk is 2.46, odds ratio is 4.73. And if I ask you, is odds ratio an appropriate measure of risk in this study design? You must tell me, no, it is not appropriate because we overestimate risk using odds ratio. The question, why do odds ratio and relative risk differ in this case? And the answer is high incidence. We have 61% in exposed subjects and 25% in unexposed. And that's the reason not to use odds ratio. Okay, one more parameter which we have to use in epidemiology and in clinical medicine is a risk marker. Sometimes you're confused about risk marker, taking it for risk factor, but actually risk marker is attribute or exposure associated with increased probability of developing a disease. So if you remember, I remind you, risk factor, presence of it increases probability of disease. Risk marker, it's just attribute that shows at increased probability, not presence of risk marker, but it's a good identificator of the risk. And obviously, risk markers are used for identifying patients at risk, and they must be used by clinicians and by professionals in public health. Risk factors and risk markers are not the same. So that is why, just typical example, yeah, risk markers are genetic risk markers. If we find that the certain patient has the certain gene that shows at increased probability of disease, we can take some in time some actions in order to control the possibility of disease development, and we just should be attentive to take precaution measures. If we have risk factor, we must do something about it. So about risk factor, we can have some intervention measures because you see in the definition of modifiable risk factors, the keyword here is that there is intervention that can change probability of disease development. And this is crucially important. Risk marker, we don't do anything with it, yeah? We just use it for our information. Risk factors are used for intervention. Now we come... I'm sorry, I don't know why my presentation stopped. Now we come to the next question, and the next question which we will discuss today is association and causation. There are a lot of studies that try not just to find risk factors, yeah, or to identify the certain exposures which are associated with the studied disease, but there are many concerns about causality. So if you read literature about identification of causes of diseases, it is obviously a very important and reasonable question. In many clinical situations, there is a question, why the patient developed a disease? And unfortunately, in non-communicable diseases, we often don't have the answer. In communicable diseases, we have the answer, yeah? And if in a communicable disease, it is similar to inspection of a criminal act, yeah, when we try retrospectively to restore the picture of a crime. So the same, we try to restore the picture of infectious disease process. In non-communicable disease, because of multi-etiological causality, it is very difficult to establish the real cause. Usually, epidemiologists use the terminology about the main cause, and we have some main cause that is probably affected by some other factors, or interaction of the risks can lead to the final outcome. So this question is really complicated, and you have to understand some terms which we will discuss. So first of all, when we deal with risk factors, causality, associations, in epidemiology we use the term exposures. It can be causes, it can be risk factors, or in most of situations in an epidemiological study, it is independent parameter or independent variable. Then we use the term outcome. What is outcome? In most of cases, it's a disease, because we study outcome as the certain pathological process. But it can be not necessarily a disease. If you study fatality, it will be death. If you study disability, it will be case of disability. If you study some external situations like traumas, injuries, poisonings, or maybe things like suicides or homicides. So outcome is in most of cases a dependent parameter or dependent variable. So the terms which we have to differentiate is statistical association and biological causation. In most of studies, we detect statistical association when one exposure or factor is related to the outcome or disease, death, disability, whatever. So to detect statistical association is relatively simple. I don't say it is absolutely simple, but we have today methods to detect statistical association. When we deal with biological causation, it's another level of investigation, which is more complicated. It requires some special studies, mostly experimental design. And when we study causation, we usually try to establish cause-effect relationship. So we distinguish levels or types of causality. The lowest level, it is called molecular, or its physiological level. Then we have personal, or it is social level. Then we have deterministic or probabilistic level. Obviously, to develop a concept about causality is quite difficult. We need a lot of studies. We need a lot of observations. And if you have causality proved at molecular level, we can predict that it can be even possible, yeah, that it can be important in the higher or upper levels of causality. If we find out that the type of causality is deterministic, it becomes crucially important because deterministic model is proving 100% development of outcome. Probabilistic model, it's like 50, yeah, it can happen or it cannot happen. So that is why the level of causality is crucially important. If you prove something at molecular level, it is usually more powerful than physiological. If you prove something at personal level, it requires investigation of biological mechanisms. If you prove something at social level, we have to search for some social factors. In most of situations, we have to answer the question, what aspect of environment, if we remove or control it, would reduce the outcome? And the practical implication of this question is very important because it enables us to control the exposure, and we want to achieve the outcome reduction by implementation of this control program. Okay, some definitions which we need to give. First of all is deduction and induction. Honestly speaking, you might have heard about these logical reasonings, and I just remind you that deduction is a reason or the reasoned argument proceeding from the general to the particular. So when you have a lot of observations, you have some rule or some kind of concept. So you apply the general rule to the specific situation. Induction is opposite to deduction, and this is a method of logical analysis that proceeds from the particular to the general, or we call it a method of generalization. Induction is much more often used in epidemiological research and in a clinical research. However, deduction is used by practical doctors. For example, when you use clinical guidelines and you have to apply the standard protocol for your particular clinical case or clinical situation. We say that in the ideal situation, what we have general and what we have specific, they should be the same. That's ideal. But in life, it's not like this. So that is why very often we have some problem in connecting what we have in a logical analysis from the general to specific and from the specific to the general. So it's important not to mistaken at this stages of giving logical reasoning. In epidemiological studies, we usually deal with a cause. So I have to give a definition that cause is event, condition, or characteristic which plays an important role, or we say regular, predictable role, yeah, that can change occurrence of the outcome. So the cause, you see, it has it produces predictable change of the outcome. It is really crucially important. So the causes, in most of cases, they fall into two groups, either genetic or environmental. In most of situations, we identify the cause at genetic level or at the level of environment. When we talk about causality, we want to be absolutely sure that the cause is related to the produced effect. So when we talk about causality, there are several models of causality. And the first one, I have mentioned it already, is called deterministic causality, when the cause is closely related to effect as in necessary or sufficient causes. What is a necessary cause? The necessary cause is it must always precede the effect. So if we have no necessary cause, there will be no effect. If you have a sufficient cause, it will be inevitably initiating or producing effect. And we have to clarify for ourselves, what is our causality. Is it caused by the sufficient cause or by the necessary cause? There are examples which show us both of them are present, or maybe neither of them are present. Another kind of cause is a component. A component cause means there are several causes which work together, and they constitute a sufficient cause for the outcome in the question. In most of cases, for example, in communicable diseases, we have component causes like biologic agent, and usually a biologic agent in the certain environmental condition creates as component causes. If you talk about non-communicable diseases, we can have component causes which are much more complicated. Let's say it's a hereditary factor plus a psychological factor, or it's a personal factor plus behavioral factor, or it is environmental factor plus habits, behavioral. And those are examples of component causes. So what about probabilistic causality? In epidemiology, most associations are not strong. We say they are rather weak, okay? And when we have relationship between the studied factors, relatively weak, and we say they are neither necessary nor sufficient, it's basically about probabilistic causality. Yeah, that is what we say maybe happens, maybe not. Maybe it will happen, maybe it will not happen. So in this situation, we often use the term of multiple causes and what we call a combination of risk factors or chain of causations when we have several risks and they can interact and they can even change effects of each other. Multiple causality is studied in complicated epidemiological models that investigate interaction of risk factors, interaction of causative factors, and we can make even some mathematical modeling for predicting the epidemiological situation. So there is one more term which we call, it is effect measures and impact fractions. When we deal with effect measure, we use parameters which we have mentioned, odds ratio and risk ratio. If we use impact fraction, we study the certain role or contribution of the exposure to the outcome, and we measure it by attributable risk. So effect measures and impact fractions are closely related to the strength of association. So if we have very high effect measure and population attributable risk is very high. So then the exposure will be a predictor of the outcome. For example, if we have population attributable risk like equal 90% or equal 100% possible or equal 85%, it means that the factor is a necessary factor in disease development. And in the class, when we make examples and calculations of risk, we usually see that the impact of some risks on the studied outcome is really very, very high. If you talk about predisposing factors, yeah, they are just increasing some level of susceptibility or some level of risky behavior. And we can have predisposing factors like age, gender, marital status, family size, education. So usually they are necessary in disease development, but they are rarely sufficient. So we say that age or gender, the fact that you are single but not married, it's not really a possible risk factor. Those are usually predisposing factors that prepare, sensitize condition, or create a situation when a person becomes susceptible. If you have about precipitating factors, they are associated with the definitive onset of a disease, illness, behavioral response, or accident. Yeah. So examples can be exposure to specific disease, amount of exposure to agent, drug, physical trauma, personal interaction, and in most of cases, the precipitating factors are necessary. So it's very important to differentiate them. Okay, when we weight the evidence, and usually it is important to weight the evidence, we say that a judgment can be done at individual level or at a population level. So when we have individual level of judgment, we use clinical situations. And let's say if a doctor deals with one clinical case, the evidence will be based on a single person. Of course, patients can be similar in result of treatment or maybe risks. So physician can combine them in a group and make a serious report. But epidemiological judgments are usually done not at individual level, but at population level, often with important judgments about the exposures that are very typical for the studied population. And when we evidence from epidemiological studies, we use the special causal criteria. Today, there are a lot of criteria which are applied for studies, for different research works, and we will discuss these research examples. The first what we need to talk about are Henle-Koch postulates. You see, they were formulated very, very long time ago, but they are really, very advanced for the 19th century. And moreover, we use them today as well, okay, because these four postulates, they don't change and they will never change. So they say that in order to prove causality between a disease agent, bacterial parasite, or a virus, or any other infectious agent, we have to prove four criteria. Yeah, we have to satisfy 4 criteria. Number 1, the agent must be shown to be present in every case of the disease by isolation pure culture. Number 2 is that agent must not be found in cases of other diseases. Number 3, we isolate the agent and we reproduce the disease in experimental animals. And then the agent must be recovered from the experimental disease produced. Postulates can be used for absolutely any disease except HIV, because HIV we cannot reproduce in experimental animals. For all other diseases, these postulates are used. If we talk about criteria for non-communicable diseases, the situation is a bit more complicated. Why? Because to prove causality of non-communicable diseases is not easy, and we have several criteria. For example, Austin-Hill's criteria, which were the first complete criteria formulated for non-communicable diseases. And we have here consistency, strength of association, specificity, dose-response relationship, directionality or temporality, biological plausibility, coherence, and experiment. So if we prove the presence of these criteria or satisfaction of them by the causal factors, we prove causality. Okay, so the next we will discuss one by one each criterion. Okay, but now we will have a short, okay, 5-minute break, or let's say not 5, it will be 7-minute break until 3:55. Okay, and at 3:55 we will continue discussing each criteria of this Hill's criteria. Так. Yeah, okay, so let's continue. So about the criteria of causality. Number one, which we should mention, is consistency. Consistency means that different studies which are conducted in different places using probably different methodology, they give similar results. So when we say that hundreds of studies have shown that smoking and lung cancer are associated, and there is no a serious study that failed to show this association, we can already think about causality. On another hand, for example, oral contraceptives, even being associated with breast cancer, this is absolutely uncertain because in some studies there is association, in other studies there is no association, there is no consistency. So we cannot conclude about causality. So number one is consistency. The best method to judge about consistency is meta-analysis. It's a really good method to test how different studies show similarity of results. And we have either exact replication of the results, for example, in experimental studies, or we have replications under similar circumstances when we study the certain phenomena, and it is crucially important to prove consistency. Number two, we call it strength of association. So strength of association means that the stronger the association, the more likely it is to be causative. And for example, if we find out that risk estimation of smoking and lung cancer is 12 or equal to 15 or equal 20, of course, we think about causality. The point is that the strong association is not just by chance, okay? And if it is not just by chance, we can suspect causality. Expressions of strength of association can be quantitative, like odds ratio or relative risk, or we can use p-value, which is used in statistical studies, and we want to have probability of chance result less than 0.05. So this is just quantitative expression of the strength of association. If you want qualitative expression of strength of association, we would like to accept alternative hypothesis and to reject null hypothesis, which we will discuss the next lecture. The next one is called dose-response relationship or a gradient relationship when increase of the dose of the exposure leads to increase of probability of the outcome. And it is really very important. For example, in many occupational hazards, there was detected dose-response relationship. When we know that the more person is employed at the certain factory where the worker is exposed to some occupational risks, the more probability of developing the professional or occupational disease. It is usually done by identification of dose-response relationship. Dose-response relationship is not relevant to all exposure disease relationship because there is such a parameter in epidemiology which we call a fixed threshold. A fixed threshold, or let's say you study in hygiene, yeah, the maximum permitted concentration of the certain substance. And then after this threshold, probably there will be no dose response. But until achieving of this threshold, there will be dose response relationship for sure. The next one is called time order, or we call it temporality or directionality, when we must be sure about sequence of events. For example, the studies have found an inverse relationship between a person's blood pressure and serum calcium. But which one is the cause and which one is the effect? So time order can be uncertain, particularly when we have a long asymptomatic stage and when the exposure may also represent a long duration of effect. So it's really very difficult to understand. In order to identify real temporality, we need to make experimental study or to make a cohort study. Another example, low serum cholesterol has been linked to increased risk of colon cancer in prospective cohort studies. But is a low serum cholesterol a cause of colon cancer? Or does an early phase of colon cancer cause low cholesterol levels? So you see, it's really difficult to find which one is a primary factor and which one is the secondary. The next one is called specificity of outcome. Specificity means we distinguish the certain substance or the certain behavior that is that makes some production of outcome different from any other outcome. Example is given here. Asbestos causes a specific lung disease, which is called asbestosis. And it is absolutely distinguishable. It's different, from many other lung diseases. But a low level of lead exposure is associated with lower rather than a distinguishable brain syndrome. So lead in this case is more uncertain as a cause because of the possible confounding effect that is not so specific effect. And let's say another example, a social economic status. It is usually not specific. We don't know exactly which parameter of low social economic status is important in inducing a disease. So that is why we think about specificity of the outcome, which should be identifiable. So then we can establish causality. Let's say here we have example which disease is more likely to be a cause of, and we have significant associations given by odds ratios for smoking, low social economic status, male gender, work with benzene, and factory employee. So you see we have disease X and disease Y, and we ask which disease is more likely to be caused by work with benzene. You see, in both cases, the risk for patients who work with benzene is equal 3. And for other parameters, it's very different. Let's say 2.1 or 1.1, 4.2 versus 0.9, or 1.5 versus 0.8. So we say that there is significant association with this exposure, which we studied. The next one is about coherence. Coherence means compatibility with pre-existing theories, and usually it's a kind of explanation that can be given to causality. And there is factual coherence when we have compatibility with pre-existing knowledge. In most of cases, researchers want to get biological coherence, like compatibility with the current biological knowledge from other species or other levels of organization. For example, if we prove that radiation produces oncologic, cancerogenic effect in rats, we say about biological coherence. Or if we deal with causality at the level of molecular, we can, or cell, we can predict the same process in the human, as the unit. Coherence can be statistical when we have compatibility with a reasonable statistical model. For example, biological coherence is presented by the serological marker of hepatitis B infection, which is associated with the high rate of liver cancer. So we say hepatitis B infection is a true cause of liver cancer, which is supported by viral genome in many liver cancers. For example, another case, which is opposite, by contrast, antihypertensive drug, reserpine, it was thought to be a cause of breast cancer in the result of studies conducted in early 1970s. But there was no other supporting biological information or studies which proved any biological mechanism. So subsequent studies which were conducted, they actually failed to support this association. The similar is for electromagnetic fields. For electromagnetic fields, there are some singular studies that prove association with oncologic process, but there is no biological coherence. There are some other criteria which we call Sasser's criteria. They are a bit similar. Like Mervyn Sasser, he used similar criteria, but he mentioned that two criteria out of previously mentioned, they have to be present for any association because they have to be really, causative, which are time order and direction. So the criteria of Sasser, they emphasize on importance of time order, which shows that X precedes Y, and directionality that X leads to Y. Sasser's criteria also say that rejection of a hypothesis can be accomplished with confidence only using time order, consistency, and incoherence. Acceptance of the theory is proved by 4: strength of association, consistency, predictive performance, and statistical coherence in the form of regular exposure effect relation. So we will not talk about details, but we can compare different criteria. Yes, there are some differences, but generally the idea remains the same. So these are some references which can be used to study more. And now we come to the last question of our lecture, is to talk about correlation and regression. So one of the most frequently used techniques or methodology in establishment of relationships between the studied variables are linear associations. So there are two reasons here why we study associations between two quantitative variables. Usually, we want to answer the question, do the variables trend to be either higher or less compared to the highest and minimum of another variable. And what is the value from a variable? What we know is actually the value of the second parameter for prediction. Yeah. So to evaluate the degree of association, we use correlation. So when we give a definition to correlation, it is obviously a linear association between two quantitative variables. And when we try to quantify the strength of association, the first thing which we have to do is to plot a graph. Okay, to plot a graph is possible if we construct the scatter diagram and we put independent variable for x, dependent variable for y. So the picture which we get is either no association when we have a scatter diagram, or we will get either very strong or maybe weak positive or negative association. So for this, we use correlation coefficient. For example, the one which is called Pearson product moment correlation coefficient. And when we interpret correlation coefficient, we will say either correlation is strong or weak, and either correlation is positive or negative. If you look at these pictures, you will see that the first two pictures show positive association. So increase of independent variable is associated with increase of dependent variable. And in negative association, increase of independent variable is associated with decrease of dependent variable. And obviously, if there are dots, or points lie very close to each other and they form a line, we say it is strong. If they don't form a line, but it's a kind of oval shape or some cloud, that is a weak association. So when we show association, we, for example, like here, between age and systolic blood pressure, we have quite strong association. When we have, for example, age and hemoglobin level, for 15 women, you see that also there is association between age and hemoglobin level, though it's not very strong. So when we look at a scattered plot, we can approximately understand is any association and how strong it is. However, to be absolutely sure, to be confident, we need to calculate coefficient of correlation, which is calculated by formulas. And the one is which is possible to use is Pearson moment correlation coefficient. So you can calculate it, and the result will lie from minus to plus 1, when 0 means no linear correlation, and minus 1 means perfect negative correlation, plus 1 perfect positive correlation. The properties of correlation coefficient are important to understand. First of all, we have to judge about the size of correlation coefficient, and the second, either it is positive or negative. The formula is used on the difference between each parameter and the mean for independent x and independent y. So we construct a table which after these calculations will give you result. So actually coefficient of correlation measures the distance of point A from the mean of x and the distance from point A of the mean of y. And these points, they show us how we show by correlation coefficient, we show how close the points are. So obviously there are some assumptions here, or we say some conditions to use this method of analysis. First of all, the requirement for using correlation technique is distribution. So we want to have normal distribution of data. Another thing is about observations. They should be independent, and for one observation, there should be only one individual and one parameter. So the formula for non-parametric method is called Spearman rank correlation coefficient. When we don't use any parameter, we use just ranks for X, ranks for Y, and number of data pairs will be N. And still this formula enables to get correlation coefficient. We can use correlation coefficient to get coefficient of determination. Its formula is to take correlation coefficient and to raise in power of 2, and we will get R square. So capital letter R square is coefficient of determination. Rxy square, it is correlation coefficient. What does it show? Usually we express it by percentage. For example, correlation coefficient equals 0.6. We raise in power of 2, we get 0.36 times 100, we get 36%. And we say 36% of variation of X is determined by variation of Y. For example, 36% of variability or variation in let's say, weight of babies is predetermined by variability of height of mothers. So coefficient of determination is very practical, and it is really very easy to use. Besides correlation, we can use regression. When we study how one variable changes under the change of another one, we not just establish strength of association, but we quantify a relationship between the studied parameters. So when we do this, we can make prediction, and this is the main application of regression technique. So usually we can plot a regression line using mathematical expression. This one is used for the linear regression when y is alpha plus beta x, where alpha is intersection of the line with the y-axis and beta is the slope of the line. And the least squares regression line, they give us the beta line with an intercept and a slope determined. In interpretation of a regression line, we usually obtain the certain prediction model, and we try to find some summary between relationship of explanatory and response variable. For example, in the result of analysis by regression, we say for one unit increase in X, Y increases by something. For example, increase of hemoglobin level by 5 points during pregnancy in low hemoglobin level women, we increase the weight of the baby by 25 grams. This is regression model. Or let's say reduction of days of stay in coma after head trauma decreases probability of death by 7%. So usually it's measured for every unit. For example, reduction by 1 day leads to reduction by 7%. That is interpretation of regression line. Usually, regression line is linear model, and it's relatively simple. We make a table for intercept and slope. However, the regression line can be sometimes not so simple. And for example, we consider that there are not just two parameters, but there are more than two parameters. We can use multivariate analysis. And then in any model, yeah, when we use a regression model, besides these assumptions, which we have that response variable y has a normal distribution for each x, variability of y should be the same through x, and the relationship between x and y must be linear, we can make inferences from a regression line. And the basic interest for us is slope, because slope shows how much parameter changes. And usually we can use all statistical techniques for interpretation of regression line. So we will talk about it in the lecture about inference. For example, a regression equation for the relationship between height and gestational age is, and we are given the formula, height is equal 97.9 plus 0.215 times gestational age at birth. So we can make prediction how much will be height of the baby born at different gestational age at birth. Usually, regression models are quite accurate and they can give us quite accurate prediction. For example, we have here parameters, and we can make prediction. But of course, there are some mathematical concepts which we have to follow, and let's say we cannot use parameter 0 in this linear regression model because it will not give us true result. Assumptions about regression we have mentioned already, so we have to control them. Precautions which are important. It is possible to obtain a regression line of any graph points scattered, but a linear regression should be applied only where there is a linear relationship. Number two, a linear association between two variables doesn't mean that there is a positive association. And may be necessary to adjust for potential confounders. Так, just 1 minute. So basically, that is all. Just one thing which I want to add. The last what I want to add is about regression analysis when we have a situation of several parameters. So if in a simple regression analysis we have only one parameter which can affect greatly the studied outcome, we also use a multiple regression analysis when there are several parameters which influence the predicted outcome. And in this case, we will have multiple regression analysis with many independent variables, like here x1, x2, x3, etc. And it is crucially important, first of all, to estimate the relationship between each parameter, x1 and y, dependent x2 and y, x3 and y, etc. Then we enter all independent variables to the model, and usually by computer software, we can identify which variable out of this x is the most powerful, is the most important in prediction of Y. So this is called multiple analysis, when we use multivariate approach. This technique is more complicated, but obviously it enables us to control interaction of factors. It enables to consider not just one parameter, but many parameters. So for this reason, multiple regression analysis is much more used compared to simple regression analysis modeling. One more type of analysis which I have to mention is called binary logistic regression. In binary logistic regression, we also study risk. And because outcome in risk assessment is usually binary, which means this is either happens or doesn't happen. So it has only two outcomes. So then in binary logistic regression, we can also identify variables which are the most important in contribution to the studied outcome. And it is really very important to perform binary logistic regression analysis when we study chronic diseases, which can be multi-causative, they can be multi-deterministic. And in this case, we will try to identify statistically significant parameters, enter them the model, and after analysis, we can get findings about the most likely causative relationships. So which will be really more advanced compared to simple risk assessment, compared to a binary logistic regression. Так, okay, so basically that's information. Okay, thank you very much. You wrote me your presence here, I see. But you know, please, because from this, from March, from the 1st of March, we have to put all the lectures to the Moodle platform. So I remind you again that you can try in the Moodle platform. There is a available internet address. You just click there and you will get to the lecture, to the video Zoom of the lecture. So that is why I understand, that some of you who probably don't come for Zoom conference, you can use this resource, but it is available only for 2 days. Okay, it's done in order those students who have maybe different time, different time in your country, and it's not convenient for you to listen to the lecture. You can use another time to listen to lecture. It's done just for this. So still, thank you very much that you give me information who is present and who is not present. I will take into account. Yes, I will mark now. But you understand, that lecture is available in the Moodle platform. Так, probably there are some questions, because today's topic is quite comprehensive. Maybe you have some questions. No questions, or maybe just no communication between us, Так, okay, so then today we can finish, okay, and our next lecture will be in 2 weeks. It will be the 1st of April, okay, the 1st of April. Так. До свидания.
До свидания.